Hello everyone, welcome to this video. In this video we're going to discuss functions and graphs and how we represent, what do we mean by a function, how do we represent a function through a graph, and what are the main types of the functions, and what are domains, what are ranges. We're going to discuss this through this video. First, what is a function? So in sciences, we have a lot of physical quantities. Let's say we have, if you want to discuss, let's say the area of a circle. Area of a circle is pi times radius squared. So we have a relationship between area and the radius of the circle. So as the radius of the circle changes, the area will change accordingly. So there's a lot of physical quantities in sciences, in nature, that is represented through relationships, such as area and radiuses, and that's how we try to form this relationship. We try to make it looks like as an equation, so that we can understand how these variables change according to each other. And this is what we call a function. So for example, we denote that the radius is independent variable, doesn't depend on anything to change, whereas the area is the dependent variable. So dependent variable, and the radius is the independent variable. Why do we state it so? Because the area depends on the radius in its changing. Okay, so if the radius changes, it's the independent variable. It doesn't depend on anything to change. Well, and this according to this equation, whereas the area depends on the radius to change. Now we're gonna denote the area or the dependent variable by a letter y, or f of x, which is a function of x, whereas the independent variable is going to be denoted by a letter x. So we say that this is y is a function of x. It's a relation of x. So area, it's a relation of a radius, of the radius. So this is how we try to make sense through equations, make sense of the relationship between physical quantities. Such as, we can say that, let's say, such as speed is equals to d divided by t. For example, if I want to study how the speed changes according to t, we can say that y is equals to x over t. The same thing. Now, what is the domain? What is domain? The domain is actually all the variables that x can variate in. So all the values, all the input values that x can variate in is called the domain. All the possible values that the function f of x or the y can variate in is called the range. So for all the values that the x can take is called the domain. All the values that the y is defined is called the range. Now, I think it will become more clear once we discuss how do we determine the domain. Now, I want just to say something, that the function takes us, if we put in the function the domain, this is the domain, the function gives us a value in the range. So for example, in our case, again, the area is equal to pi r squared. If we know the radius, we can get the area. So let's say if the area is the domain, let's say x is equals to 1 in this case, then the area is gonna be equals to y equals to pi. If y, let's say, if x is equals to 2, then the y is equals to be 4 pi. So the duty of the function, sorry, this is x is equals to pi. The duty of the function is to take us from the domain ran to the range ran. Now how this happens? Usually we have some functions where the domain can be, let's say, for example, 3x. If I have a function y is equals to 3x, x can, okay, this is example 1. X can be from minus infinity, can belong from minus infinity to plus infinity. There is no problem. The x can take any value of these. And because x can take any value of these, the y also can be from minus infinity to plus infinity. So the domain ranges, the values of x ranges from minus infinity to plus infinity, whereas the range also from minus infinity to plus infinity. There is no restrictions. There is no restrictions in the domain. And this is what we call, this is the domain that has no restrictions. We call it, this is a natural domain. This is what we call by a natural domain. Now, as I said, sometimes we have restrictions on the domain. For example, if I have a function, a relationship between y and x, f of x equals to y equals to x squared. The x can take any value. X can take any value from minus infinity to plus infinity. There is no restrictions on x. However, if I put any negative value here, let's say x is equals to minus 1. So minus 1 times minus 1 is equals to plus 1. So the range is different than the x. The range is different than the domain. So the y, the possible values of y is gonna be from 0 to plus infinity. So here the domain has no restrictions. It can go from the values of x can variate from minus infinity to plus infinity, whereas the values of y can variate only from 0 to plus infinity. This is another example of determining the range and the domain. For example, another example can be given. If we have f of x, a function, f of x is equals to y is equals to 1 over x. Now in this case, I have a restriction on the values of x. So x cannot be equals to 0. X cannot be equals to 0, because if we have x, we cannot divide by a number which is equals to 0. So the domain of x ranges between, okay, minus infinity to 0. 0 is not included, sorry. So minus infinity to 0, this bracket means 0 is not included. Union 0 to plus infinity. That's the domain. That's the accepted values of x. Whereas the range in this case, also because I don't have an input value of 0, the range in this case is going to be minus infinity to 0, union 0 to plus infinity. Again, we can have another example, which is y is equals to, for example, this is an example, f of x is equals to y is equals to radical x. Radical x. Now again, radical x must be equals or more than 0. X should be positive. under the square root, x should be positive. So the domain of this value, the variation of x for this function, is from 0 to plus infinity. Okay, 0 in this case is included. We don't have any problem of including 0, whereas the range is gonna be also 0 to plus infinity. There's no restrictions on the range. Now, things can become more, let's say, more complicated. Let's take this example, which is things where things are more complicated. In example 5, if I have, let's say, y is equals to radical 4 minus x, and I need to know to expect how the x values variate, what's the domain of this function and what's the range of this function. Well, I can say that here 4 minus x should be equals or less or more than 0 because it's under the square root. So 4 is should be more than or equals to x. So x is less than or equals to 4. So the domain x can variate for the values of minus infinity up to 4. The range in this case, there is no restriction on the range. The range can variate from 0 to infinity, to plus infinity. I can have even more complicated example, which is, let's say if I have number 6, example 6, if I have y is equals to 1 radical 1 minus x squared. So the same thing I have to say that 1 minus x squared should be positive, then 1 should be more than x squared. So x squared is less than or equals to 1. So x squared is, so I'm talking, I want to get the values of x. So x is less than or equals to 1, or x is more than or equals to minus 1. So the values of x here x takes the value between x1 and minus 1. So the domain in this case, the domain here, x can variate only between the accepted values of x, so that the square root is defined. The accepted values is between minus 1 and 1. So the domain here is minus 1, 1. So here, if I want to know the range, now I want to replace the values of x to get the maximum value. So if I replaced, let's say, if I want to know the range of this function, how the y values variates, what are the possible y values, what's the range of this function. So if I replace, let's say, minus 1, let's say 1 minus 1 squared, so I'm gonna get 0. 0 is an accepted value, so you can minus 1, 0, and 1. So 0 is an accepted value. If I want to replace x is equals to 0, this is x is equals to minus 1. So minus 1 minus 0 is radical 1, so it's equals to 1. Try to replace all the possible values. You're gonna get that the range for this function is gonna be between 0 and 1, and the 1 is included. This is how we calculate, or how we find the domain of a function, the range of the function, how the domain and the range of the functions are different. So basically, we need to look at the square roots, at the denominator of a function, the denominator, and we can calculate things easily, and we can determine the domain and range. Again, for example, if I have in drawing the graph of a function, for example, if I have y is equals to x squared. Let's say I have this function, and I want to draw the graph of the function. I want to represent this function through a graph. So let's say I have these possible values of y, and these are the possible values of x. So if it was 1, the y will be 1. If I replace x by 2, if I replace x by 2, then this is 1. Then y is going to be 4, because this is y is equals 2 to the power 2, which is equals to 4. If I replace the x by 3, the y is going to be 9, because 3 to the power 2 is equals to 9. If I put the x is equals to 0, the y is going to be equals also to 0. So let's draw this function. This function is going to start from here, 0. Let's take the negative values. If I have minus 1, the function is going to be here 1, because minus 1 times minus 1 is equals to 1, because here minus 1 squared. Minus 2 is going to be equals to 4, because minus 2 squared is equals to 4. And if I have here minus 3 is going to be equals to 9, because again minus 3 squared is equals to 9. So let's draw this function. It starts from the origin, 0, 0. Here we have 1, 1. And when the x values were 2, the y values were 4. When it was 3, the y values were 9. And this is how the functions look like from the positive values of x. Let's look at the negative values of x. Minus 1, it was 1. And minus 2, it was 4. And minus 3 is equals to 9. So this is the value. And then these are the negative values of x. So this is how the function f of x y is equals to x squared looks like if you want to represent this function as in the graph. Sometimes let's say that sometimes we have representations of, we have a function which changes its values according to the domain. For example, let's say that I have a function f of x that takes the values is equals to minus x when the domain is x less than 0. It's x squared when the domain when x is between 0 and 1, and 1 when x is more than 1. So sometimes the function is described by using different relationships and different parts of the domain. How can we represent this kind of function? We treat it like this is the same thing, but we treated different domains have different relationships, and then we go, let's solve it. So for example, if the x is negative, so we're dealing with this kind of domain. We're here, right? So if x is negative, it's minus x. So if f of x equals to minus x, this means that if minus 1, because x should be negative, so I need to variate in these values. So minus 1, f of x is going to be 1, right? Minus 2, f of x is going to be 2, because here f of x is equals to minus x. So I need to multiply it again. I need to multiply it by 2, by negative. So minus 3 is going to be 3, minus 4 is going to be 4, and etc. and so forth. So the function is going to look like this. This is the function. Now let's go to x squared. X squared, it's gonna look like a curve, and we already showed that in the previous case. Now, if x equals to 1, the f of x is gonna be equals to 1 no matter how the function varies, no matter how, the x varies. No matter how the domain varies, the y is gonna be equals to 1. So it's gonna be horizontal straight line. So here is gonna be as 2, 3, 4, 5, x, as no matter how x varies, y is gonna be all the time is equals to 1. And this is how the function, this function is represented. This is how it's represented. And this is once we, sometimes functions have different relationships in different domains, and this is how we represent it through the graph. Now, I need to discuss the even functions and odd functions. Even functions and odd functions. Actually, this kind of even function and odd function, it comes from the power. The power functions. Power functions, we're gonna discuss this later on. Once we have even power, then it's gonna be an even function, and odd power is gonna be an odd function. So let's take this, and from its definition, the definition of even function is that if I have f of minus x, if I replace the value minus x, I'm gonna get the same value of y as x. For example, let's look at our case, which is x squared. X squared, f of x equals to x squared. If I replaced minus 1 for x is equals to minus 1, so f of x is equal minus 1 times minus 1 is equals to 1. If I replace x equals to 1, then f of x is equals to 1 times 1, which is equals to 1. So we can say that we can conclude that f of minus x is equals to f of x. Once we come to conclude that f of minus x is equals to f of x, this means that it is an even function. It's an even function. An even function, as you can see here, this is an even function, which is x squared. Y is equals to x squared. This is an even function. It's symmetric, as you can see that it's symmetric around the y-axis. It's symmetric around the y-axis. And I can't have a value x, y, unless I have a complementary value which complements it as minus xy. So if I don't have a point in the function xy, I can, like for example, if I have a 3y in my function, let's say this point is 3, 4, then I should get from the other side minus 3, 4. This is for the even function. An even function, if the condition to have an even function, which is symmetric around the y-axis, as you can see here, it's symmetric around the y-axis. The condition for an even function is to have f of x equals to f of minus x. Let's do the same thing. Let's try to define the odd function. The odd function is whenever I replace f of minus x, I'm gonna get minus f of x. For example, x to the power cube. So if I have f of x is equal x cubed, x equals to minus 1, I'm gonna get minus 1 times minus 1 times minus 1, which is equals to minus 1. F is equals to 1, then I'm gonna get 1 times 1 times 1, which is equals to 1. Let's use a non-trivial example, which is, let's say x is equals to 3. This means that 3 times 3 times 3, which is 27, or x is equals to minus a 3. So minus a 3 times minus 3 times minus 3 is equals to minus 27. So this is an odd function. Apparently this is an odd function because it satisfies the condition of the odd function. It satisfies that f of minus x is equals to minus f of x. Minus f of x. Here in this case, we need to the odd function, as you can see here, that it's symmetric around the origin. Odd functions are symmetric around the origin, as you can see from the graph. And the condition to have each point xy has a complementary point minus x minus y. So if I have a point, let's say 2, 4, in an odd function, I will have, okay, a complementary point minus 2, minus 4. This is an obligatory in an odd function. Now let's view some examples of functions, and let's define it whether an odd or an even. For example, let's have another function which is f of x is equals to x squared plus 1. And the question says that, is this an odd function or an even function? So the first thing is I want to replace minus a negative value, and then I'm gonna see what's the output. So if I say x is equals to minus 1, then minus 1 times minus 1 plus 1 is equals to, minus 1 times 1 is equals to 0. And okay, so I'm gonna get a 0 value, so that's not gonna work. Let's say f of x, let's say x is equals to 3, minus 3. So I'm gonna get minus 3 times minus 3 plus 1, which is 9 plus 1, which is equals to 10. And I'm gonna get x is equals to 3, which also 3 times 3 plus 1, which is equals to 10 as well. So we can say that f of minus 3 is equals to f of 3. So f of minus x is equals to f of x. This means that it's an even function. Now another example, let's say that let's work on another example, which is a simple function, which is f of x equals to x. Let's say I want to know whether it's an even function or an odd function. So I replace, let's say it's a very trivial example, but let's work it on. So if x is equals to minus 2, then, and x is equals to 2, for example, then f of x is, minus, okay. So f of minus x is equals to f of x, then this is an odd function. Now we have sometimes, let's say f of x is equals to x plus 1. So just replace, let's say that I have 9, or x is equals to minus 2. So f of x is gonna be equals to minus 2 plus 1, which is equals to minus 1. And let's say that x is equals to 2, then f of x is gonna be equals to 3. Okay, so this is neither odd nor even because it doesn't satisfy one of these relationships. So this function, we can say that this function is not odd or even. So it's not necessary to have an even function. It's not necessary to classify all the functions by either odd or even. In this case, we have a function which is x plus 1, which is neither odd nor even. Now we'll discuss special functions which are common functions. We will start with the linear functions. The linear functions are the functions that take the form of mx plus b, where m and b should be constants. In some cases, b can be equals to 0. If b is equals to 0, then the function passes through the origin. Again, if m is equals to 0, then the function f of x equals to constant. This means that the function y doesn't variate with x. This is one form whenever we have m is equals to 2 to x equals to 1. This is how the function looks like whenever we have a linear function that takes the form of mx plus b. Now, if b is equals to 0 and m is equals to 1, then f of x is equals to x. This is called identity function. So it's as if like defining, identity function is as if defining y, defining the f of x. Now, the proportional relationships, and what are the proportional relationships and what are the inversely proportional relationships? The proportional relationships is whenever we have a constant multiplied by a multiple of the constant. So for example, if we have y is equals to kx, and whenever x changes, y changes according to multiple times, which is k, to x. For example, if I have y equals 2x, if x changes by 1, if x changes by 1, then the multiple of 1 multiplied by 2, then y changes by 2. Usually, as in the proportional relationships, as you can see that, not usually, always, as x increases, y also increases. Whereas the inversely proportional is whenever we have, it's proportional to the reciprocal of x, and you can see that a inversely proportional relationship is as if we're saying y is equals to k over x. Now, if x increases, y decreases. It's important because also once we define two physical quantities, it's good to identify if it's inversely proportional relationship or a proportional relationship. For example, if you have a speed is equals to v equals d divided by t. Now the speed and distance are proportional. As distance increases, the speed increases, whereas as time increases, the speed decreases. So this is how we're talking about the instantaneous. Like, it's just a rough example. Another example of a common function, which is a power function. Power function here, it's any function that takes the form of x equals to x to the power a is a power function, where x, now we're varying the base here. We're gonna see that next. We're gonna exponential functions where we vary the power, but now here we're varying the base. And it's important to know the classes of this function. So we're gonna take the first example. If a is equals to an integer, n is equals to 1, 2, 3, whatever. So we're discussing the function. The function is gonna look like x to the power 2, x to the power 3, x to the power 4, etc. and so forth. Notice that x can take the domain here, x can take any value. It can vary from minus infinity to plus infinity. Whereas the range in the odd function, here we have an odd function, the range can be from minus infinity to plus infinity. But in even functions, the range is from 0 is included, to infinity, to plus infinity. Again, notice that as the power increases, here the value from -1 to 1, the curve tends to flatten as the power increases. You can see that. You can look like whenever we have x to the power 2 and x to the power 4, you can view how the curve tends to flatten from the values -1 to 1. And you can see the steepness of the curve from 1 to infinity. The steepness of the curve increases as the power increases. As you go from x to the power 2 to x to the power 4, the steepness of the curve increases. And that's logical. Now, this is for a, for the values of a is equals to integers. Now, what happens if the values of a is not equals to integers, is equals to, to negative values? For example, -1, -2, etc. So technically, we're discussing the f of x is equals, x minus 1, which is equals to 1 over x, and f of x is x minus 2, which is equals 1 over x squared. Now what's gonna happen? How are we gonna deal with it? Now the domain here, in this case, the domain, we cannot accept x should not be equals to 0 because it's in the denominator. So the domain here is gonna go from minus infinity to 0, union 0 to plus infinity. What's the range in this case? How does the range variates? Now the range in 1 over x, this function represents 1 over x. You can see that as, and then let's discuss first the positive values of x. As x increases, y decreases. Easy, because this is inversely proportional relationship. As x increases, the y decreases. Now here, the x can take a value of equals to 0, so that y also can take a value is equals to 0. And as x increases, y tends to 0. As x tends to infinity, y tends to infinity. Now here also, here we can have a negative value. Why? Because if you take x equals to -1, then you're gonna get f of x equals to -1. If x equals to -2, then f of x equals to -half. So as you can see that as the x-axis, as the x increases in the negative sense, the y decreases also in the negative sense. So it's somehow the symmetry of this curve. It's somehow the symmetry. If you plot it, it's somehow the symmetry of this curve. This is not the case for x is equals 1 over x squared, because we can't have a negative value here. Y cannot have a negative value because we have an even here. We have 2 power 2. So you're multiplying negative by negative. So you're gonna get all the time you're gonna get a positive value. So for this reason, you're gonna get the domain for these two functions is gonna be from minus infinity to 0 union 0 to plus infinity. The range for this one is gonna be from minus infinity to 0 union 0 to plus infinity, and the range in this one is gonna be from 0 is not included, sorry, 0 is not included, so from 0 to plus infinity. This is the power function when we have a negative value of a minus 1, minus 2, etc. Now, the trigonometric function are functions. We're gonna discuss two values here, two functions, which is sine x and cosine x. How to represent if we have a trigonometric relationship between x and f of x. How it's represented through the graph. So basically, all what you have to do is the following. We're gonna need to define the domain. Domain x can take any value from minus infinity to plus infinity. There is no restriction on x. But the range of the functions, the two functions, they're gonna range between minus 1 and 1. We know that the range of the trigonometric function, the cosine x or sine x, it takes the value between minus 1 and 1. Now, if you look at, like, for example, sine 0, it's gonna be equals to 1. Sine pi over 2 is gonna be equals to 0, and that's how the curve looks like. You can see the curve of the sine looks like this sinusoidal shape. Now we shift in the cosine. It's a little bit shifted. We start from the origin 0, 0. We shifted by pi over 2. Somehow by pi over 2, you can say that for cosine x, cosine 0 is equals to 0. Cosine pi over 2 is equals to 1. And this is the trigonometric functions. Last, but not the last one, actually we're gonna talk about the exponential function. Now we're not variating the base. In power functions, we used to say that x to the power a. We were variating the base. Now we're variating the power itself. So we're variating the power itself. There is a condition for the exponential function, is that the base should be positive and should be not equals to 1. Should not be equals to 1. The domain, which is the values of x, can be from minus infinity to plus infinity. Can take any value. There is no problem. There is no restrictions on this, because you're gonna get any value is defined. Now the range here is positive. The range of x, the range of y, which are the values of y, the answers for this function, the output of the function, they're gonna variate from 0 to plus infinity. There is a common point, as you can see, this point between all the values, all the exponential functions should pass through this point, which is for x equals to 0. This means that a to the power 0 is always equals to 1, no matter what a is. 3, 4, 10, 2, no matter what a is, the x, if the exponential a to the power 0 is going to be equals to 1, and you can see that all the functions are passing through this point. The last function that we're going to discuss is the logarithmic functions, which take the form of log base a to the power x. Again, should be equals to 0, should not be equals to 1, and it's a positive constant. A should be a positive constant. Actually, the logarithmic function is the inverse of exponential functions. That's exponential functions, and thus you can see that easily by the shape of the curve itself. And if we need to discuss about the domain, there is restriction on the logarithmic function. The domain should start from 0 is not included to infinity, don't have a value of x at 0. And the range can be from minus infinity to plus infinity. There is no problem. The range can take all the negative values to the positive values. Now, also there is one common point in all the logarithmic function, which is this point. You can see that if x is equals to 1, log ax is equals to 0. So because log a to the power to 1 is equals to 0. This is a common point in all logarithmic functions. You can see that how the logarithmic functions rises and how the exponential functions rises. You can see that. This ends this video discussing some of the functions and the representation of these functions through 2D graphs. Hopefully it was beneficial, and thank you for watching.